Hello everyone and welcome back to my How To Education channel. As I promised you before the beginning of the summer vacation, here is the first quantitative business video. How to Ace Quantitative Business Introduction to Linear Programming. After watching this video, don't forget to leave me your feedback, letting me know if you want me to add this subject to the regular weekly postings. So what is linear programming and why to learn about it? First of all, I know that this title might sound scary, negative, or at least a little worrisome. After all, the expression linear programming might remind you of computer science, computer engineering, calculus, or computer programming. Nevertheless, the point of this video is to actually clarify this misconception and to show how powerful of a tool linear programming can be. There is no better way to begin this lecture than by defining the term linear programming. Linear programming is defined as a course of action that needs to be taken in order to find the best solutions to certain management and operation or production problems. The best solutions are what we call optimal solutions, and the management and operation or production problems are those that involve a production process with a restricted or limited amount of resources. Therefore, it is important to learn about linear programming so as to be able to allocate the constrained resources in a way that avoids wasting and optimizes the production process. So far, we have seen that linear programming is a tool used to solve managerial and operational problems. What does this mean? Does it mean that we can use this method to solve every single problem that arises? Well, technically, you could. Nevertheless, in some cases, these problems are so simple that there are other easier ways to solve them. Let's now tackle all the possible ways of solving a managerial or operational situation. In order to solve a problem, we must obviously be able to identify it and define it. This is what we call the problem statement definition step. In other words, after observing the environment and situation, the second step for solving a problem is to be able to formulate a problem statement. After observing the situation and defining the problem statement, it is the time to create a model which will be used to find and implement a possible solution to the matter at hand. This picture shows step-by-step of the problem-solving process. But what is a model and why do we need to build a model to solve a problem? A model is a way to portray an existing problem in a format that makes it easier to be seen and understood. Let's say, for example, that it costs $15 to manufacture t-shirts whose profit margin should be 33% of its costs. A model that can be used to calculate the price of a certain number of t-shirts could be y equals 15 plus 0.33 times 15, all of it times x, which is 15x plus 4.95x. Thus, y equals 15x plus 4.95x, such that x is the number of t-shirts, which can take any value greater than or equal to 0. Y is the price of X t-shirts. Therefore, the value of Y depends on the value of X, and this is why we say that X is the independent variable and that y is the dependent variable. 15 and 4.95 are the constants, also called parameters. Now that we found out what a model is, let's incorporate this model into an existing problem. Assume that the t-shirts mentioned previously are made of cotton and that there are 40 pounds of cotton available. It takes 0.5 pounds of cotton to make one t-shirt, and all the cotton must be used rather than be discarded. Thus, if there are X t-shirts to be manufactured, 0.5 pounds per t-shirt cannot exceed 40 pounds used in total. That is, 0.5x equals 40. We can finally say that we created a model composed of two relationships, y equals 15x plus 4.95x, such that 0.5x is 40. The price equation is the objective function and the resource is a constraint. From a seller's perspective, the aim of the model is to maximize the price as much as possible without decreasing sales. That is, maximize y equals 15x plus 4.95x subject to 0.5x equals 40. This was a very simple model to solve. If 0.5x equals 40, then x equals 40 over 0.5, which is 80. And if y is 15x plus 4.95x, then y is 15 times 80 plus 4.95 times 80, which is 1596. In conclusion, under the availability of 40 pounds of cotton, knowing that each t-shirt needs 0.5 pounds, the optimal quantity to be produced is 80 t-shirts. The optimal selling price per one t-shirt is 15 plus 4.95, which is $19.95, which makes it a total of 1,596 for all the 80 t-shirts. This is the maximum price the seller can charge without decreasing sales. A common approach used to build and solve a model is the break-even analysis. The purpose of such kind of analysis is to find the break-even point. In other words, the amount of units that need to be sold for the total revenue from sales to be equal to the total costs incurred. Since profit equals total revenue from sales minus total costs incurred, the profit will be zero at the break-even point. The break-even analysis aims to provide managers with a point of reference when taking decisions. When conducting a break-even analysis, one has to deal with the following components. Number 1, quantity, which means the number of units being sold or produced. It is denoted by Q. Number 2, costs, which means the total costs incurred and are denoted by TC. Cost has two components, variable costs and fixed costs. The variable costs are the ones incurred according to the number of units produced and are denoted by VC. The fixed costs are the ones that have to be incurred whether or not there is production and are denoted by FC. TC equals FC plus VC. Revenue. Revenue means the total revenue from sales. It is equal to the selling price of one unit multiplied by the number of units sold. It is denoted by TR. TR equals PQ. Profit is equal to the total revenue from sales minus the total costs incurred. That is PQ minus FC minus VC. Let's suppose that the fixed costs of operating a shop are $15,000 per month and that the variable costs are $12 per unit. Each unit sells for $32. If the amount of units sold per month equals 600 units, find total cost, total revenue, and total profit. Well, total revenue equals price per unit times quantity sold, which is 32 times 600, which is $19,200. Total cost equals to fixed cost plus variable cost, which is equal to fixed cost plus variable cost per unit times quantity, which is 15,000 plus 12 times 600, equal to $22,200. The profit equals total revenue minus total cost. So 19,200 minus 22,200, which is minus 3,000, which is equivalent to a loss of $3,000. If we assume that the price stays the same as well as the fixed and the variable costs, then the only part of the model that is changing is the quantity Q. This means that Q is the variable and that price, fixed costs, and variable costs are parameters. Since we're doing a break-even analysis, we need to find the amount of units that need to be sold for the total revenue from sales to be equal to the total costs incurred, leading the profit to be zero. We know that profit equals total revenue minus total cost, which is price times Q minus fixed cost minus variable cost per unit times quantity. Since profit is zero at break-even, and since we said that price, fixed cost, and variable cost stay the same, this means that we always need to find the variable Q. Thus, 0 equals price times Q minus fixed costs minus variable cost per unit times Q. To solve it, we put fixed costs on the other side, since fixed costs is the only parameter that is not dependent on Q. Thus, fixed cost equals P times Q minus variable cost per unit times Q. Solving this equation yields Q to be fixed cost over price minus variable cost per unit. Thus, the break-even point Q equals to fixed cost over selling price minus variable cost per unit. This previous formula can always be used to find the break-even point. In the case of the previous example, 0 equals 32Q minus 15,000 minus 12 times Q. 15,000 equals 32Q minus 12Q. Therefore, Q equals 750 units, which means that at 750 units, total revenue equals total cost and profit equals 0. For the previous example, we have worked with the premise that the parameters are always constant. Nevertheless, in real-life scenarios, parameters do change frequently. If the parameters change frequently, we can conclude that the solution of the model might change as well according to the change of the parameters. To study the changes of a model, we use a process called sensitivity analysis. Let's now examine the modifications made to the previous example. Suppose that the selling price increased from 32 to 39. A higher price might increase or decrease total revenue and consequently profit, depending on the product or service being sold. Let's suppose that for this example, we have an elastic good. That is, if prices increase, the quantity demanded by people tends to decrease. In this case, a higher price will make it more difficult to sell the product. Thus, in the case of an elastic good, the only valid justification for a change in price would be an increase in the costs incurred to manufacture that good. For example, let's suppose that the raw material needed to manufacture the product needs to be replaced by a higher quality raw material. This will naturally result in an increase in the variable cost per unit manufactured. Let the variable cost per unit be $15 per unit rather than $12 per unit. In this case, the break-even point would become fixed cost over selling price minus variable cost per unit, which is 15,000 over 39 minus 15, which is 625 units. Therefore, the new break-even point is 625 units rather than 750 units. Let's suppose now that the selling price will continue at $39 per unit and that the variable cost per unit will continue at $15 per unit. In addition, there was an increase of $6,000 to the rent plus other utility expenses. What would the new break-even point become? The answer is rent and other utility expenses are what we call fixed costs. That is, they need to be incurred whether or not production takes place. In this case, the fixed costs that were 15,000 will increase by 6,000 and become 21,000. The new break-even point will be 21,000 over 39 minus 15, which is 875 units. All of this lecture and its examples were solved manually using algebra. This means that we were dealing with the mathematical model. For the upcoming chapters, we will be tackling other ways to find specific information such as the break-even point and to build and solve models. We will also discuss how to implement the solutions found to the everyday management of the business. Our attention will be mainly on the graphical method, which consists of finding data such as the break-even point through the help of a graph that can either be done manually or through Excel. Excel in this case would be a combination of the graphical method with the computer method, since the solution will be found not only through the use of a graph, but also through the use of Excel programs and add-ins, such as the goal-seek function and the Excel QM. More details to follow in the upcoming lectures. This is it from Quantitative Business for this week. But if you have reached the end of this video, it is because the content is helpful to you somehow. If this is the case, then don't forget to give your friends and acquaintances the opportunity to have access to these videos by liking, sharing, commenting, and subscribing. The intent of this first video in Quantitative Business is to evaluate how many people will appreciate this new subject before I include it to the 2023-2024 academic year schedule. Thank you so much for watching it, and see you soon with this new academic year's calendar.